T rotor is equal to 1/2 vector theta dot phi dot transpose M rotor times the vector theta phi dot equals 1/2 theta dot transpose phi dot transpose. So I get this matrix S minus 1, J, S minus 1, transpose, S minus 1, J, J, S minus 1, J, theta dot, phi dot. Where J equals diag n1 squared I z z1, so diagonal matrix. That's what I mean when I write the word diag. So zeros in the off diagonal, all the way to n squared I z z n is the inertia matrix measured after gear reduction. So, these little electric motors don't really have much inertia to speak of before gear reduction, but as soon as you do a 200-to-1 gear ratio, all of a sudden they have inertia. And the matrix S relates the axes of rotation of the motors with respect to each other. So let's write that up.
S minus 1.
S minus 1, but yeah, it should be S, probably S minus I. I probably should have written it right. It's like the matrix S, so yeah, thank you. S minus I there would be much better. Thank you for that. So I have the elements of S, I, J given by 1 if J equals I. So that's the diagonal. BI transpose BJ over NJ. If J is greater than I. We're taking rows and columns here. So if the column is greater than the row, so you're talking about the upper diagonal. And 0 if otherwise. So in our two-link planar robot, this is pretty simple. BI transpose BJ over nj is just equal to 1 over nj, so that's not really a difficult term. Remember, these are unit vectors that tell us how things are rotating. So if you have a planar robot, this one is 0, 0, 1, and this one is 0, 0, 1. So if you have 0, 0, 1 transpose times 0, 0, 1, you're just going to get 1. It's not a big deal. The only time when these come into account is if I added in that extra rotation into my shoulder. So I had a 2-degree freedom joint, then that B matrix would actually be changing all the time as I move my arm up and down, right? And then I'd have to take that into account. So these would actually become like time-dependent things, right? But in my planar robot, I don't have to worry about that. And that makes this formulation pretty complicated. So you might actually, there's actually a whole bunch of different ways to write down the equations for a robot. There's like no one correct solution. So the way I'm doing in today's lecture just happens to be really good for the 2-link planar robot. But when you get really complicated robot configurations, this particular method doesn't necessarily turn out to be the best way to do it anymore. There's a whole field of study called multi-body dynamics. People get into the best ways of writing out dynamic equations for complicated multi-body systems. And this is not necessarily the best way to handle a really complicated system. Although theoretically it would work, but just things get complicated, that's all. So potential energy stored in the spring is U spring equals 1/2 theta minus phi transpose K theta minus phi, where K is a diagonal matrix of spring constants. So I really shouldn't say spring constants because they're really joint stiffnesses if I want to be technically correct. Because usually you're not really talking about a literal spring, but in this case I don't mind saying spring constant because the robot in my lab actually does have springs, so definitely call them spring constants for the robot in my lab. So the friction terms are going to have, you're going to have friction kind of separately in these different subsystems. So friction terms include damping in the spring, which we'll call ds, damping in the links, d theta, and in the rotors. So Lagrange's equation results in m plus s minus I j s minus I transpose j s minus I minus I j times theta double dot phi double dot vector plus f of theta dot phi dot minus s dot j transpose theta dot plus ds plus d theta minus ds minus ds plus d phi multiplied by theta dot phi dot plus k minus k theta phi plus g of theta 0 equals 0 u. Then to find what f is, where f equals c theta dot plus m dot rotor theta dot plus 1/2 di by di theta dot transpose phi dot transpose m rotor theta dot phi dot transpose so I wrote down an expression for m rotor before, so this one's already in your notes. That was the one that had the s minus i's in it.
Is that G matrix or G of theta?
That's g theta. So let's make sure we have, I'll wait till you write those equations down and then we'll see if we can have some intuitive understanding of what's going on inside these equations. So they all have like physical meaning that we can interpret. Okay, so this is what I would call the inertia matrix of the system. So I call it the system inertia matrix. Okay, so it's kind of like the mass in a system that's moving, except we have a rotating system, so it's full of rotational inertias. So you can see that this term here is going to relate, blink acceleration to the forces that are applied to the robot. And this one is going to relate the acceleration of the rotors through J to the forces applied to the robot. In this case, mostly to U, my control. So my control is going to have a direct effect on phi double dot, right? And these are kind of like the off-diagonal terms of the matrix. So, it still does directly affect the links as well through this off-diagonal term. So you also have the kind of cross-coupling, you might call it, between these two coordinate systems. So there's definitely kind of interaction that's going on between these two coordinate systems. What should we delve into next? So this is the damping matrix here. So this is all the friction that's going on in the system. So obviously I used a linear friction model. So this isn't exactly representing reality. In reality, friction is a pretty non-linear kind of thing. Especially static friction is particularly tricky. So here you're kind of assuming that the robot is kind of really well built and well oiled and well machined, so that friction is approximately linear. And in fact, what we'd expect to see is that there's not much friction in the spring. The flexi-spline really shouldn't have damping in the flexi-spline. It's basically a flexible element. There's not a whole lot of damping there. The friction really comes from like a rotating shaft here. Like these are both rotating shaft ideas friction, so they will probably be significant, much bigger than you would get here. This is my spring forces here. So there's a K and there's a negative K. So the whole idea is we can, there's equal and opposite reaction. So the spring flexes. When it flexes, that creates a torque on that joint, but it also creates a torque backwards. It's going to create a torque on both links. So there's kind of the equal and opposite reaction there. This is gravity pulling down on the robot. Gravity acts it's in the top equation here. So gravity is acting on the links directly, not the rotors. So the idea here is that you could argue that the rotor shaft is affected by gravity somehow, but it's not really a big effect. You'd have to have some kind of asymmetry in your motor, but it would be a tiny effect. So really, it's the links that are affected by the gravity directly. And then we talk about F over here, good old Coriolis and centrifugal forces that we've seen before. So we're familiar with this term here. This is M rotor, but it's M rotor dot. So remember, M rotor kind of has these kind of terms there. We have all these S minus I's places. So, like I said, in a two-link planar robot, we're talking about S as a constant, because you just, it depends on these unit vectors, but you just have 0, 0, 1 and 0, 0, 1, and therefore S is constant. So, in our case, this is just going to be 0. Like, it would only be if you had an extra degree of freedom in your shoulder joint, where you could actually change those things, that you'd all of a sudden get this term. And same thing here, you have di by di theta of M rotor, but M rotor is just constant. So this whole term is also going to be 0 for our simple robot. So these things would only pop into more complicated robot configurations where you have more degrees of freedom than we have in this one. Okay. So let's just write that down, I guess. So a note for two-link planar robot, d by dt of M rotor is equal to 0, and di by di theta of M rotor is equal to 0, since each bi is just equal to 0, 0, 1. So it turns out like nonlinear control theory is a little bit limited in designing, U for this model. If someone gave you this model and asked you to design U to follow a trajectory, it turns out this is actually kind of a difficult problem. Maybe you believe me. It's not that easy. So to say design U for this system and get really accurate tracking turns out to be kind of hard, mainly because of these cross-coupling terms here. When you do your project, ideally you implement this system of equations to model your robot for kind of testing purposes. But if you can't get this working for whatever reason, don't worry about it too much. So what we're going to do is we're going to do a simplified model of this robot. So with the simplified model we're going to come up with, we can, one, design a control system, and two, have a bit simpler simulation. So ideally, you could design your control on, even if you design your control on a simple model, you can still try it out on this model, because you can, certainly simulate this whole model. But so, like I said, if you don't get this working, you could just try it out on the simple control model on the simple model, and make sure you get that working. You may want to do that first and get it working, and then try it out on this. So, this is more, MATLAB symbolic math, playing with until you get these equations to work out, which, you may or may not struggle with, depends. I think what will probably help you out, I think I'm allowed to, photocopy, one chapter of a book. So I might photocopy one chapter of a book and put it on D2L so you can look at it, and then at least you're not looking at my messy handwriting and whatever mistakes I put in and whatever mistakes you put in extra when you're copying them down might make it hard to get something actually working. So I'll photocopy the chapter of the textbook and put it up there for you so you see a bit neater derivation of this. But let's talk about the simple model robot now that we can much more likely to be able to design a control system with. So we'll do what's called Spong's assumption. So I should say assumptions that first assumption is that gear ratios are large. In this case, Nj is really big. So this term in S is approximately equal to 0. So anytime I saw a term like Si minus j, that would also be approximately equal to 0. So those are my cross-coupling terms here. So those cross-coupling terms of my inertia matrix disappear, which makes things really much, much easier. Robots do have large gear ratios, so this is a really safe assumption. This is Nj is typically at least 100, could be hundreds. So we are talking about a really small number. And just remember, these are just like 0.001. So you're talking about like 0.01 or less. So it's not a big thing to ignore in a model. So my second assumption will be the rotor inertia before gear reduction is negligible. And 3, in other words, like an electric motor shaft, just really doesn't have much inertia compared to the rest of the robot. It's just very small little shaft, very little inertia in it. The damping in the spring is negligible. And that's a pretty good assumption. There's you get a lot of friction in a shaft that's rotating, and you have to put oil in because it's our ball bearings that are oiled to get the shaft to rotate freely. There's still a lot of friction in there. The actual friction in a mechanism like a spring is very small because you're talking about the actual inherent friction in the kind of molecules that being attached to each other. You're not talking about something rubbing against something else. So it is really much, much smaller. Then the simplified model becomes m of theta times theta double dot plus c of theta dot times theta dot plus d theta dot plus g theta plus k theta minus phi is equal to 0. Oh yeah, I forgot to, maybe I should actually explicitly write down that I was talking about the robot that we're dealing with m rotor is constant, so I don't know if that's an assumption, but just to write it down. M rotor is constant. So I don't have to end up with those f terms anymore. So j phi double dot plus d phi dot plus k phi minus theta equal to u. Okay, so this is kind of what we'll return to later in the course. So what I'm going to do for the next couple of lectures is talk about designing controls for rigid robots, and then I'll come back to this flexible joint robot model, and we'll talk about designing controls for the flexible joint robot. Okay, so I will revisit, it'll be I think like 3 lectures from now before I come back to this equation again. But you can kind of see how this works. You have, this is kind of now nice intuitively how it works, is that you have your control torque coming in from the motor. There's also a torque that's caused by the spring as well. There's some friction in the system, and that's what's deciding what your phi double dot is. So basically the rotation of the shaft is determined by damping a spring force and input torque from a motor. So it's kind of nice, simple, easy to intuitively understand equation now, right? And then you have the dynamics of the links, and basically this term you can think of as like being the kind of control term now. So this is like the spring, and this is going to be measured in torque. So the spring constant times the deflection, you're going to get units of torque here. So this is a torque that's created by the spring, and you can see that basically if our control system can create the correct difference here between the link angle and the rotor angle, then we actually can control this torque. So for this equation, we'll kind of treat this term as a control term. We'll try to design it to control these dynamics. And then to get the desired control torque we want here, we'll just design U to make sure that phi goes to its correct value, to make sure this is what we want it to be, right? So that's what we're going to do. It's called backstepping. We're going to do that in a few lectures. But like I said, for now, for the next couple of lectures, we'll concentrate on designing nonlinear controls for rigid robots, and we'll see how that works. So I'll return to the rigid robots. So I'm just going to throw up the code here up on the screen in case people have any questions about the rigid robot code I gave you. Oh, by the way, any questions about flexible joint robots before I throw up this rigid robot code? So like I said, ideally in your project, you'll design your controller probably with this set of equations. And then ideally, you could test it on this set of equations too, but it's better to test it on the full set of equations. So I'd rather see you do that. But if you only get it working testing on these equations, that's okay. It's not a requirement to test on the full complicated model. And there really shouldn't be much difference at all. Probably so little that you probably even to see it might not be possible. So any questions about the flexible joint before I go on here? So I did put this README file in that, was among all those files, so hopefully you found this. And so that's kind of the first thing to read to figure out what all those files do. And kind of the big thing is I'm starting off by deriving the robot model using MATLAB symbolic math. I'm not actually starting right from Lagrange's equation, but you could do that yourself just to verify it's correct if you're interested. But I do, basically create a numerical model using like symbolic math, algebraic model is essentially what I'm doing. So I like doing it that way. I mean, it's not the only way you could set it up, but it kind of makes sense to me to do it that way. And then once these kind of nonlinear robot functions are and I also created a linear model for you. So if you're interested in like designing an LQR control, I mean that's like one line of code in MATLAB. You type in like LQR AB. Well, I gave you AB, right? So you actually have there's no work to develop the matrices AB for this. So you can literally design the LQR control as like 3 lines of MATLAB code. Obviously, you have to pick Q and R as well, but. So if you know what an LQR control is, it should be pretty easy to set up once I give you the A and B matrices. Don't feel you have to do that. If you've never heard of LQR control before, you can just do a PID controller. I said you should have a linear control working by your time your seminar comes around. So if you just have a PID controller working for that, that's totally fine. And then it's not down here till I get the actual instructions of how the main program is set up. So it's set up so that it can be compiled into C code so it runs fast. There's no requirement for you to do that whatsoever. If you want to work just in MATLAB and never compile it into C ever, that's totally fine. There's no requirement to run anything in C. It's simply for your benefit that you can run things faster if you want to. But it does take some extra debugging, so if you get it working debugged in MATLAB and you don't feel like taking the time to get it working and debugged in C Coder, it's totally fine. There's no